There's a PhD thesis published now based on this interaction of science and politics and the media. And I can give you that reference later, but it's a very interesting thesis, and it concentrates mainly on the political aspects of it, and also the politics of the big journals like Science and Nature and how they react to premature release and how the pressure was on from NASA for premature release of the data, and it's a very interesting story.
Do you feel comfortable just saying briefly how that all happened with the premature release?
The White House released the story because of a guy named Dick Morris, who was an advisor to the president and who had apparently whispered it to his female companion, who called the tabloids and revealed it and got it all wrong, but it came out. And when that story started to come out, the CBS and the networks started talking about it. And at some point, NASA said that we don't want this to dribble out in the tabloids. We have to have our press conference and release it properly. And I was on vacation and on camping on a river in Central Texas, and I was contacted to get my behind to Washington for this press conference, and to heck with my vacation. And so that's what happened next. And science was not happy with it. The journal was not happy with it, but they accepted it. And after negotiation between science, the journal, and the NASA public affairs and top management. So it was all very, I think most of the story is in that book, in fact. All right, so let's move on to the magnetites. Because I want to point out, and I'll be happy to discuss some of these other features with you about the size of the fossils, or microfossils, whether they're really microfossils. I'll be happy to discuss the other contamination issues with you. We essentially wrote papers that disproved all those contamination issues. And those are all published, and in fact, nobody disputes that anymore. Nobody argues that any of this stuff was formed in Antarctica anymore, although those were big arguments at the time. The only controversy that is really left here, and aside from the morphology of the possible microfossils, which I can get into in a minute, but the main controversy has been the origin of the magnetites. And we argued that these magnetites were formed on Mars. Nobody takes exception to that now. And furthermore, that they were detrital. That means, in geologic terms, it means that they were washed into the carbonate and were deposited there in cracks and crevices. And there may have been some of these bacteria, magnetotactic bacteria, in there, but there were also a lot of magnetites which are not necessarily associated with the magnetotactic bacteria. And so how do we know all that, and what is the evidence for that? Okay. All right, this is just a picture of the rock itself and some of the magnetite carbonate globules. We call them pancakes now because we finally realize they're mostly rather flat, like pancakes. They're not globular. And we can show, I think, and I'll show a few pictures to support this, that there's a lot going on. These carbonates are some of the most complex carbonates that have ever been studied, and these have been studied by more than 100 research groups throughout the world.
Dave, I'm sorry, can you go back to the picture before? forms. I went through that in class a couple of weeks ago, but could you just explain what they're seeing on the right again?
Okay, on the right, those little gold parts are the cores of the carbonates. Those are mainly calcium carbonate with some magnesium and some manganese. The dark bands are the iron-rich bands, which are also mainly carbonate, but are full of these magnetites. The white band is a magnesium carbonate, which has no color in it, and is fairly pure. And then the outer dark band is another magnetite-rich layer. Now, there's also some zoning in the interior of the cores, but for example, the very center is usually enriched in manganese. Now, we're still trying to understand the details of all this zoning. Well, we understand how it goes, but we're trying to interpret it. It's hard to interpret in detail. Okay, there are a number of features here. I've already talked about the zoning. I'll show you the chemistry. This is a chemistry of one of these features, showing for example, the manganese-rich layer in the interior on the left, showing the iron-rich layers, and so forth. This is a standard electron microprobe dot map, which is not real clear because of the black background. The one without a label on the bottom is sulfur. This is a drawing or a cartoon of how these things really are. The one on the left is an actual SEM picture with the carbonate artificially colored in. The one on the right is what our critics have been able to produce in the laboratory. And the difference is that ours, the real Allen Hills one, is always embedded in a pit, a form-fitting pit. And that does not occur in the laboratory versions. In the laboratory versions, the carbonate forms in cracks between two pyroxene surfaces. And why is that? That's fairly critical. And our hypothesis is that pit is made by the microorganisms, and it's made by acidic dissolution enhanced by biology, so that pit is actually dissolved into the pyroxene by the microbes. That's our hypothesis. And they're always like that. We've never seen them like the ones at the right. And that can be seen in some of these detailed textures. These are all carbonate surfaces. And all the carbonates in Allen Hills show some water dissolution. The carbonates are where two parts of the meteorite have pulled apart, and it leaves these little carbonate discs somewhat embedded in the surface. And in every case, the surface of those carbonates has been somewhat weathered or dissolved by water. This shows a very abrupt region between the iron-rich carbonate on the right and the pyroxene or silicate on the left, to show that this is where the carbonate is sunken into the pyroxene, and this is what you get if you look at the top of that pit. The pit is filled with carbonate, and the pyroxene on the left is not particularly modified, but on the right you see that the carbonate is there and it's been modified. I'll get back to some of that in a moment here. This is another part of it. This is the rim between the magnesium carbonate on the left and the iron-rich outer rim. In other words, between the white part of the Oreo cookie and the black part of the Oreo cookie. It's a very abrupt boundary on the scale of essentially tens of nanometers. It is not a gradational boundary. It is extremely sharp as these things go. And that gets into our argument later that these things have not been heated. They have not been heated after formation, or that boundary would have blurred together by diffusion of the elements because of the heating. The point being that this is an extremely sharp boundary, and that tells us something. This is simply the texture of the pyroxene on the left, away from the carbonate, and on the right, the carbonate is colored brown, but what you see on the right is underneath the carbonate, where part of the carbonate is broken away. You can see it's a different texture. It's different between underneath the carbonate and the pyroxene on the left. What's that mean? Well, it means, we think, that there's been a different process working on the right-hand side of the screen. There's been possibly organic acid there, which was not on the left. And that remains to be shown, but that is our hypothesis for that difference. This is a closer view. On the top is the surface where the carbonate's been broken away. And you can see it's got a very complex texture. And we think that texture is a result of the acidic dissolution caused by the acid associated with the carbonate. And on the left is the carbonate itself, and you can see how the two fit together. We have actually done a detailed study of these carbonates with the TEM using the focused ion beam or the FIB technique. We've cut little slices of them here and there and looked at the slices. And this is a cross-section of one of those slices. And there are several interesting things. The iron-rich area has been colored in brown. The uncolored part is the magnesium carbonate with magnesite, and it is those brown parts that contain the magnetite. And we're trying to figure out how that works. This shows where the slices are made. And this is the detail, again, of one of those slices. And what can we learn from this? All right, number one, these carbonates are multicrystalline. It's not one big crystalline. They're polycrystalline carbonates. And you can see the different textures there are different crystals in the carbonate. Number two, there's not much porosity in the carbonate. If we looked only at the top, we would see a lot of porosity. It looks like Swiss cheese. But when we cut it with this focused ion beam, it is fairly compact and not porous. And this gets into how it was formed. It had to be formed by crystals growing together and filling up the space. And again, the dark areas are the iron-rich magnetites. This shows the low porosity, even at the tens of nanometer scales. This shows that there's some sulfur-rich cross-cutting veins here. Again, we think that the original carbonate was shattered up and water flowed through it and deposited stuff. And that stuff includes sulfide minerals and some of the magnetites. The very interesting part of these magnetites is that they're embedded throughout all these parts of the carbonate that I've been showing you. That is, the iron-rich magnetites are found in the center, and they're found on the rims. The difference is one of abundance. And that gets into how they got there, how they were formed. We would argue that they're not formed from the material that was already there. And that's what our critics have argued for several years in a number of papers that they're formed directly from the material that was there originally, the carbonate. This shows that in the iron-rich rim, there are a lot of magnetites, which are all those little dark speckled things,